Okay, so now what we're going to do is we are going to get into graphing piecewise functions. So what I have here is I have 4 different functions that I am going to show you how to graph. I did mention that they are continuous, so therefore there's not going to be any breaks in the graph. But you can see that for each of these, we have two different graphs that we're going to have to combine. And then in addition to that, we are going to identify the domain and the range, because you can see that the functions are restricted based on their domain restrictions. So I'll show you a couple different ways we can go about this. One main thing that I talked about with graphing piecewise functions is it's very important to make sure you understand the parent function as well as understand the transformation. So if that again is something that you feel weak on, make sure you kind of have that sheet with the parent functions on it as well as the transformation, so you can kind of refer to it as I'm working through these problems. All right, so one of the first ways that I like to teach graphing piecewise functions is just to first forget about the domain restrictions, okay? And just think about these as 2 different functions that we're going to graph on the same sheet of paper. Y equals 2x minus 1. I'm going to actually zoom in one more. And the graph, y equals negative 2/3 x minus 1. Okay, and let's just graph them both on the same sheet of paper, and then we'll kind of come back to the work. So notice here that my kind of scaling is going by 1/2, so therefore that's a 1, and that's a 3. I made a mistake earlier because I wasn't paying attention to my restriction, or I wasn't paying attention to my scaling, so just want to make sure you have that kind of worked in there. That's positive 3. Okay, so if I wanted to graph this blue graph, then I can see my y-intercept is at negative 1, which is going to be down here, and you can see my slope here is like 2/1. So I'm going to go up 2. So that's 1, right? So that would be up 1, and then that'd be up 2, and then over 1. So it'd be right there. Or I could go down 2. So that'd be up 2. So that's going to be, where am I at? I'm like making myself go crazy. These graphs are confusing me. All right, if I'm at negative 1, going up 2 is going to go to 1, and then over 1 would be right there. I could also go down 2, and to the right 1. Okay, so now let's go and connect that graph. Jeez, oh man, having a hard time graphing the easiest function of them all, a line. All right, now let's get into the purple. Same thing, same y-intercept, negative 1. But now this one is going to be down 2, and then to the right 3, since it's negative slope. Or you could go up 2 to the left 3. Okay, and then I'll try to graph that as best I can. Not too bad. I'm getting a little bit better with this. Okay, now obviously if you were to throw these graphs together just like this, they would not be a function because they would immediately not pass the vertical line test. You pass the vertical line, boom, they don't pass the vertical line test. So therefore we have to restrict the domain there, right? So now we need to kind of go back and look at the domain restrictions. And the domain restriction says, for the function 2x minus 1, which is the blue graph, I only want to graph that when x is less than equal to 0, or I'm sorry, when x is less than 0. So anything to the right of 0 for this graph, anything where x, remember the x-axis here? Here's the x-axis. So when x is going to be positive, that's not going to be defined for my function anymore. So I got to somehow graph that. Now, it is going to be an open circle, which we'll talk about here in a second. But nothing to the right is going to be defined for that function because that's my restriction. Now, for the purple graph, on the contrary, this is saying all values that are greater than or equal to 0. So, on the other hand, this purple graph is basically going, the purple graph is going to be for all values at 0, so I'm going to fill that in, and then going to the right. Okay, so therefore that's how that equation is going to look. And then again, if you want to go ahead and check your answers, we can go and look at that. Let's just go and pull that up real quick so we can kind of see what that looks like, just to make sure we got that correct as Desmo's waiting up. So what I did here is I just labeled them. I put them in folders on the domain, but you can see here that's the piecewise function. If you want to look at the rules that I did, I provided each rule as well as its restriction, but that's just so you guys can kind of see those on that. So we'll kind of come back to that. We'll check all of our answers here to make sure I don't make any mistakes. The next one is Sine of X. So Sine of X is obviously something that should not be very familiar with many of you. So the important thing for Sine of X is it has a max and a min at -1 and 1. It's a bounded function. It's going to cross right there, but that's saying for only x values that are less than 0. So obviously I'm not going to be graphing this perfectly correct. I'm just going to kind of like do a rough sketch here, but the graph is going to look something like that. Now the other way you can go about this is you could continue graphing all of sine, but since I know that x has to be less than 0, I'm just going to kind of stop. And I'm not going to graph anything to the right. The same thing for the quadratic function. Like I know what x squared looks like, right? It's a parabola looking like that. But why graph where it's negative if I know that I only need to graph where the x values are positive? Now, obviously, that's helpful. Sometimes, like for a line, it's not very easy, or sometimes the functions, you're not very aware of what the graph is going to look like. So you just want to graph the whole graph and then delete it or erase it, which is the method I used here. Other times, you can just go ahead and graph the two functions and graph the two functions based on their constraint. So if I was going to graph x squared, it's now, again, this is x is less than, so therefore that's going to be an open circle. But then if I wanted to do this, I'm going to fill that in, and then I'm just going to draw a nice little parabola. Now, I did forget to talk about the domain and range, so let's go and look over that again. All right, so in this function, the domain. Remember, the domain basically on graph is saying how far to the left is the graph going, how far is the right graph going. And you can see that this graph, as it's going to expand, it's going to continue going further left and right. So therefore, the domain would be from -infinity to infinity. The range is basically saying how low is the graph going to go to how high. And you can see that the maximum value that this graph has is -1. So my range is going to be from -infinity, and -1 is included. So therefore, I'm going to use a bracket. All right. In this example, now again, you'd have to kind of understand the parent function to know that the minimum value there is -1, for at least for the range. So when looking at the domain now, again, you can see this graph is going to continue to the left and continue to the right. So my domain is going to be all real numbers. But my range is now going to be from -1 to infinity, because it's going to continue going up, but the minimum value there is -1 because that's bounded below. This function is bounded above, increasing and increasing. This one is decreasing, increasing, decreasing, increasing, kind of crazy. All right, let's go and look at some other ones. So now I'm kind of changing it up. Now my function is changing at x is greater than 1. Now, typically, sometimes that can be confusing, but when you actually look at the graph, a lot of times the transformations are going to match where this discontinuity can be. So don't really fear, so much as far as, if it's not at 0. Because I look at this, if I want to graph y, or the square root of x minus 1, that's just a horizontal shift 1 unit to the right. Oh, let's check my answer here, right? I forgot to kind of do that. So if I go and check my answer for B, you can see that's what the graph looks like. Kind of looks kind of cool, right? Weird, but it kind of looks cool. All right. So let's go back to this one. Now, again, we're going to be shifting 1 unit to the right. So I'm going to take my square root function, which I'll do in the blue, and I'm going to shift 1 unit to the right, and then I'm just going to be the curve. Now, I shouldn't have drawn a dot there because it says x has to be greater than 1. So therefore, I'm going to use a big, nice open circle and then graph my square root graph. It's going to look something like that, right? Roughly. I'm not trying to be exact, so don't say, oh, it needs to go through that point. I understand. I'm not going to be perfect on there because it's technically at 3. That would be 4, so that would be like up to there. So, all right, fine. I know people are going to be, it should be at 3. It should be at 2. Okay, you're right. So let's graph it. So see, now my curve's all messed up. So doesn't look that good. But either way, you can see the 0.34 is defined there. The next one is the absolute value function, which is the V-shaped graph. Again, we are shifting it 1 unit to the right. I now have a vertical stretch, and it's also being reflected about the x-axis. Now, this is for only values that are going to be less than -1. Let's just look at this graph again. It is defined at 1. It's the V-shaped graph. So instead of going to the left 1 and down 1, it's going to be to the left 1 and then down 2. That's kind of like what that vertical stretch is going to do if you remember graphing transformations. right? However, we're not graphing anything that is to the right of y equals 1. Like here's that vertical line 1. Anything to the right of that, we are not going to graph. So I am just going to erase that portion of it. And then we can just go back to Desmos and make sure that we did that one correct. And you can see there, yes, it's a nice little line, and then it kind of curves. All right, so now let's do the last one. Now the last one here has 3 functions, but that shouldn't deter us. All we're going to do is treat each one separately. So I just need to add a different color here, right? So let's do 2x plus 5. Well, that's just a line. Cool, we can do that. So my 2x plus 5, oh man, I'm getting like right on the opposite. Now I can't go any higher, so now that has to be less than -1 here, right? So I see like -1's right here, so rather than like going up to the right, I'm just going to want to follow this graph going down. So I'm at 5. If I'm going to go down 2, that means I'm going to be at 3, down 2, over 1. And then I can go down 2, over 1. Now again, I could continue drawing this graph and then erase where it's greater than -1, or I can just say, all right, x has to be less than or equal to -1, so I'm going to make a nice big dot, and then I'm going to follow the curve, that way, or something. Try to get there. Good. All right, let's see if I can delete that bad curve. Dang it. That wasn't supposed to happen. Let's try this again. Okay, it looks better. Please don't mark me down for bad graphs. I'm just trying to do my best. The next function is 3. So again, sometimes this gets confusing students. Like, how do you graph y equals 3? Well, wherever x is, y is equal to 3. Now, it's important to understand that x can only be between -1 and 2. Well, here it's an open circle, but thankfully this other function had it filled in, so I don't need to worry about that. But it's going to be from -1 to 2. And then we'll leave a nice like open circle, okay? And then the last example is -1/2 x plus 4. So let's see, let's go ahead and graph that as like a red function. So I'll go up to 4. Now here's like an example where I'm gonna need to graph this. So I'm gonna go down 1, and then over 2, and that is going to fill it in because x is greater than or equal to 2. So then let's just follow that pattern again, down 1, over 2. My graph would look something like that. Why do I keep on forgetting to do the domain and range? Let's go and check our graph here real quick just to make sure I did that one correctly. And you can see, yep, we're looking pretty good. Now let's go back and identify the domain and range for both of these. So here you can see the domain is continuing to the left, continuing to the right. So my domain is going to be from -infinity to infinity. And my range looks like the graph is continuing going down and continue going up. So that's going to be -infinity to infinity. In this example here, you can see the domain is again expanding to the left and to the right. So my domain is going to be from -infinity to infinity. And my range looks like we have a maximum value of y equals 3. So my range is going to be from -infinity to 3. And it looks like 3 is included, so I'm going to use brackets. So that's when we have piecewise functions that are connected. And you can see that each of the graphs that I did are all nice and connected, and that helps kind of makes identifying the domain and range rather simple. So now what we'll do is we'll look at some examples of when we have piecewise functions that are not continuous.